Hi, suppose you're asked to design a digital decision-making assistant for a medical team. The goal of the assistant is to help the team to make correct choices about interventions, treatments, and diagnosis. Using the available knowledge in the right way, it should provide an answer or a decision that the team can trust. Its reasoning should be transparent and understood by the team. In this way, the team can ask the assistant to explain every recommendation they don't fully trust. Your first task is to take current knowledge from articles, reports, databases, and other sources of information and organize it so that the assistant can use it to make its recommendations. You must ensure that the resulting knowledge will give to the assistant all the features requested by the medical team. You might be already thinking about a solution to this problem. Well, today I would like to show you a framework that solves this problem: description logics. Description logics are languages designed to specify facts and rules about our topic of interest that can be processed by a computer. By design, they're meant to provide many, if not all, the functionalities our assistant needs: correctness, reliability, transparency, and efficiency in making automated decisions. Let's have a look at a simple example to see how description logics allow us to take a piece of information and turn it into knowledge that our assistant can use. Let's start by looking at some facts that we might find in our sources. SARS-CoV-2 is a virus that causes the COVID-19 disease, or Comirnaty is a vaccine that prevents COVID-19. We noticed that the three nouns SARS-CoV-2, COVID-19, and Comirnaty are used to refer to three specific objects or entities. We might want to think of them as units of our knowledge. In description logics, we call them individuals. There are other nouns, though, that talk about categories of objects, such as virus, disease, and vaccine. We can think of them as categories of individuals, or concepts. Finally, we notice that there are also verbs or actions that talk about relationships between individuals, like causes and prevents. These are roles that individuals take for one another and form the third basic ingredient that a description logic needs, together with individuals and concepts. Using these building blocks, we can now start to organize our knowledge. We start by representing each individual as a node in a graph. We label each individual by the concepts that describe it. Finally, we connect individuals using roles to represent the relationships between them. We can now read the facts we started with off the graph. And yeah, knowledge written using description logics looks more like this list of assertions. As we will see later, though, the graph we created is not only a way to visualize facts, but also what the assistant will use to get to the meaning of our knowledge base. We have seen how to use description logics to specify facts about individuals. Our sources of information also contain more general statements, such as a vaccine is a treatment and prevents some disease, or a virus causes some disease or symptom. We can use description logics to model these statements as well. Here we already chose which concepts and roles to use as building blocks for our knowledge. Now, we can specify how these building blocks can be combined using logical connectives like conjunction and disjunction, in addition to operators that relate concepts and roles and that we call restrictions. The resulting expressions are called concept descriptions. Yes, the syntax may look unfamiliar, but the meaning is intuitively the same. In the first sentence, we have a description that talks about individuals that are treatments and prevent some diseases. In the second one, we have a description referring to individuals that cause some diseases or symptoms. The last step that is left is to combine these descriptions to create rules. And rules in description logics take the form of inclusions between descriptions. They look like implications. If an individual is described by the left-hand side of the inclusion, then it must also be described by the right-hand side. And this is exactly what we need to model our information. To us, these rules read the same way as the natural language expressions we started with. But now, together with the facts we encoded before, They can be processed by the assistant and used to automate decision-making. But what is the meaning of this knowledge for the assistant? The unit of meaning in description logics is what we call a model. You can think of a model as an extension of the graph we introduced earlier, that respects all the rules and the facts contained in the knowledge base. For the assistant, the meaning of knowledge is then the set of all models of the rules and facts it knows about. Having a way to give meaning to knowledge is what allows the assistant to come up with recommendations and to explain how it reached them. Description logics are designed to actively put knowledge into use. An agent can process a knowledge base written using description logics and automatically perform reasoning tasks. These typically fall into two categories: decisions and explanations. An agent could decide that its internal knowledge is consistent, that is, check if it has some models. It could decide if a given statement is a consequence of its internal knowledge, or that is, if it has truth in all of its models. Once the agent made a decision, it could explain to the team how it used its facts and rules to come to that conclusion. The ability of the agent to execute these tasks heavily depends on which description logic is used to structure its knowledge. And description logics come in many flavors, each with its own set of features. Some are designed to be very detailed and expressive. Others are designed with performance and scalability of reasoning in mind. There is an inherent trade-off between the expressiveness of a description logic and the computational complexity of reasoning with it. The more features we use to encode our knowledge, the harder it will be for an assistant to use it to reason. In extreme cases, no assistant will be able to use it correctly. On the other hand, to achieve the best performance, we will need to give up many modeling capabilities that will give us a more detailed knowledge. As a knowledge engineer, it is important to understand this trade-off and to choose which description logic best fits the requirement of the project. So far, we have seen what we can do using standard description logics in our process of capturing and organizing knowledge. However, we might find ourselves in need of more constructors to express quantitative information. Consider the two following pieces of information, which we might find in a journal article or a textbook. Virus X causes disease Y with an estimate of 59 to 63%. Or if region A is part of region B, then B has more viral units than A. One of the sentences expresses uncertain information. The other refers to measures of a quantitative flavor. While standard description logics might make it hard to express these statements, there have been recent efforts to provide quantitative extensions to model information of this kind. One of them comes in the form of conditional probabilities between concept descriptions. The other introduces concrete domain restrictions, where the term concrete emphasizes that we have the ability to talk about specific, concrete values. With these extensions in place, we are confident that we can model all the knowledge we need to build our assistant. Our task is mostly done, and we can happily call it a day. Or can we? Let's take a step back and consider the trade-off between expressiveness and performance again. Constructors like conditional probabilities and concrete domain restrictions seem to add a considerable expressive power to our standard description logics. We can then expect, following the spectrum, that reasoning with them will be more complicated for our digital assistant. So we need to ask ourselves, do we really have to use these extensions? Or could we express the information we need without having to resort to this? To reply to this question, we need to find a way to compare the expressiveness of different description logics. This is where I step in as a description logics researcher. My goal is to study ways to compare the expressive power of description logics with quantitative extensions. To show you how I do this, let's go back to our task of building a knowledge base for our digital assistant. And suppose that among our sources we have some precompiled knowledge graphs. Some of them are taken from real-world cases, and so we want to take them as the truth. Others are examples of wrong diagnosis or generally misleading knowledge. So we want to take them as false. And to make an example, a misleading piece of information might simply say that SARS-CoV-2 is the primary cause of hair loss and skin rash. What description logic can we use to distinguish the correct graphs from the wrong ones? In other words, what description logic can we use to build a knowledge base that will only describe the correct graphs as its models? For standard description logics, there is a way to answer this question. To illustrate it, I will need the help of a game board and two friends that are willing to play. We craft the game board by taking two graphs that we want to compare. Player 1 will then be the spoiler. Their goal is to find a move that cannot be replicated by player 2. Player 2, on the other hand, will be the duplicator, and their goal is to mimic each move made by player 1. The two players can choose several games to play using this game board, each of which is associated to a description logic and comes with its own set of rules. If the spoiler can find a way to win at one of these games, it means that the two graphs can be distinguished using the description logic associated with it. If the duplicator is always able to win at that game, then the two graphs cannot be distinguished using that description logic. So, let's say that the two players select a game in which player 1 starts by putting their token on a random node and is able to play subsequent turns by moving their token along the edges of the graph. In this game, player 2 must make sure that, mimicking the moves of player 1, the node they choose for their token has the same symbols as the one chosen by player 1. I can tell you that in this game, player 2 has a winning strategy, that is, a playbook that tells them which nodes to choose to mimic the moves of player 1 and always win. This means that the description logic associated to the game cannot distinguish the two graphs. But if we change the game and gave player 1 the ability to move backward, suddenly player 2 wouldn't have a winning strategy anymore. Player 1 is now able to make a move that cannot be replicated, and it finds a way to win the game. The corresponding description logic can now distinguish the two graphs. This tells us that the description logic used in the first game is less expressive than the one we used in the second game. And this is how we can use games associated to description logics to assess their expressive power, provided that we have such games, of course. Earlier, I told you that each game is associated to a description logic. This is true for standard description logics, where we know exactly which games are associated to which languages. And this means that we can use them to understand if the logics are expressive enough to model the knowledge we have. For description logics with quantitative extensions, we do not know the full picture. In my research, I wear the hat of the game designer, and I use theoretical mathematical tools to show that certain games can be effectively associated to the quantitative extensions of description logics we saw before. My goal is thus to complete the picture. Here, I kept most of the mathematical infrastructure needed to talk about my research out of the scope. But if you're interested in getting to know the topic at a deeper level, you can check out some of the articles that are linked in the video description. Now for the recap. In this lecture, I introduced you to description logics and showed you how they can be used to structure knowledge. I've also shown you how to extend them with quantitative constructors and how to compare the expressive power of different languages. I hope you enjoyed this lecture and that you will be able to use the insights gained here to work on your next project. Thank you for the attention.